For example, you see these green lights, right? These are the southern lights. We also see northern lights in the northern sky towards the Arctic, North Pole, you know. And you take a picture, yes, nice, pretty pictures. Here it's seen green. Again, it can be red, blue, other colors. So to explain that, now we need help of physics. And not just physics, atomic physics. You know, when the charged particles from the sun, they are constantly bombarding the Earth, and we have a protective shield of magnetic fields that guides these charged particles towards the pole, and hence we only see these borealis in either the North Pole or the South Pole. Okay. We'll come to more physics of it later in the chapters. Here, this is a night sky, picture of a night sky to not just night sky, the whole 24 hours as seen from Antarctica, the southernmost hemisphere. This central point is the celestial pole. We defined all this last class period, online class. Earth rotates, it has a rotation axis, right? That rotation axis points towards our celestial sphere or towards the celestial pole, north celestial pole, south celestial pole. And so when as Earth rotates, there's one point directly to the center that does not rotate. It lies within the rotation axis. And any other stars, they rotate around that central point. If it is in the North Pole, that's where our northern star or the North Star would be. And all other stars, they simply rotate. And since it's in the South Pole, these stars do not set or rise. We see the whole of the stars rotating about that central point. And this is a time-lapse image taken for whole 24 hours. If it were at the, some other latitude from Earth here, so this is north. If you are at the equator, we actually see all the stars rise and set from east to west. Okay, but from the North Pole and the South Pole, we don't see them rise and set. We see the whole circle. Even the sun, you're in the Arctic, the sun kind of doesn't actually rise from the horizon. It grazes through the horizon, goes up, and again towards the horizon. It never goes down the horizon. And that was all night sky. And the days, even in the day sky, because the sun is so bright, we don't see any stars. The atmosphere is lit up with all the photons, light particles from the sun. It obscures every background stars. We don't see it. The only chance we see is during the solar eclipse, when the sun is completely blocked by the moon. And so during the day, we don't see stars. However, this is the day sky, daytime, and we know sun rises and sets every day. But there is a lot than that. The geometry, the dynamics of it, we'll explore it more in the coming days. But one thing to keep in mind, the degrees of it. If this morning sun rose at some point in the east, and next day it's not going to rise from the exact point. Okay, that point moves by 1 degree, either to the left or right. Okay, it depends on what day of the year it is. You know, so when it's the shortest day, which is December 21, you know, it's at the, let's say it's at the rightmost region point, and every day after that, the point where the sun rises moves to the left 1 degree, and in the longest day it reaches the farthest point to that 6th month, which is June 21, and then it moves back again. Okay, so and why that happens, we need to understand more orbits, orbital dynamics. Again, we'll explain that as we go. And the other thing, the other important term, the ecliptic. Okay. I hope now you all have memorized or know what celestial sphere is. It's the projection of the sky above us. It's like a dome around us, and it appears that every stars and sun are, you know, embedded into that dome, into that sphere, and they rise and set. And so is the sun. So sun takes this path in the sky all year long, right? And so if we project that path and, you know, draw an imaginary circle in the sky, that's called the ecliptic. And we say the sun moves around, goes, or sun always follows that path called the ecliptic. But again, remember, it's apparent motion. That's what it appears. Because sun is at the center. Just with respect to solar system, sun is stationary at the center, and the planets move around. Because of that motion, the rotation and the revolution of the planet, it appears that sun is moving in the sky, but it's not. Okay, that's important. And so this is a diagram that explains the daily motion and the annual motion. So there are two types. The daily motion of the Earth, which is caused by the rotation, or rotates in its axis. Here, this is the Earth. It has rotation axis. So I can take anything. This can have a rotation axis. If it rotates like this, its rotation axis can be at the center, or its rotation axis can be at the edge. Then it will rotate like this. If it's at the center, it will rotate about that rotation axis. Okay. And here, and the other one is the annual motion caused by the revolution. Okay, here are two terms. First was the ecliptic, then the rotation of the Earth, the rotation about its axis. The other one is the revolution, the motion of the sun, motion of the Earth around the sun. It goes around 1 year. That's the revolution. Sometimes we use this, especially the term rotation, quite loosely. Meaning we say the Earth rotates the sun in 365 days. We say that. The rotation. In fact, we're talking about the revolution. Okay. It depends on the context. But I'll try to be specific with rotation and going to use the revolution. And and also again, sun moves 1 degree east every day. Again, that is measured with respect to something. Okay, that's the measurement. We need to have some reference point. Okay, so when I say, I am 5 meters, I'm standing 5 meters from what? From where? This matters. I'm not 5 meters from this table. So I have to say I'm standing 5 meters from the central table. So that central table is my reference point. Okay, so same way, let's say this is day 1, August sometime, and next day, August 2 here, if you look at the same time of the day, sun has moved 1 degree in the sky, and what can be the reference? We can reference it to the background stars. So, like this one here, these are the background star, also the ecliptic constellation. They are also called the constellations on the ecliptic. Now we know what ecliptic is, the projection of the path of the sun in the sky, ecliptic. And there are, behind sun, there are planets and stars. Right? Because all the 7 other planets go around the sun, so there are also planets because they all rotate almost in the same plane. So when we see from Earth, we see sun, another planet, and also all the stars. So what is behind the sun? Planets, and moreover, there are plenty of millions, billions of stars. So when sun is here, let's say you are a star, sun is here, and I see you as one of the stars. But position changes of the sun. So sun gets to that position, let's say the evening, and now the star behind the sun is a different star. Okay? And not just one star, it's a group of stars. And we call these group of stars constellations, or especially the Zodiac constellations. There are 88 different constellations in the sky. I'll come to constellations more in the next slide. But there are especially the 12 constellations that sun passes through in a year's time, depending on what month. Okay. And I should have more. So again, for here, same diagram. Here is a chart. So between January 21 and February 16, Capricorn. So here is the Capricorn. So the Earth would be behind it here. And when we see sun, right behind the sun would lie this constellation Capricorn in that month, January 21 to February 16. That's how you get your constellations. I am Taurus, May 10, May 13 to June 22. Here, so Earth goes around